Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor IARE Hyderabad. So in previous module we had seen the loads acting on the structural components, then function of structural components. So now in this video we will see what types of load on the structural joint. So this will be the topic of this video. So we will cover in this video. First one is the type of a structural joint, what are the types of structural joints, then type of load on the structural. So just see here, type of loads on the structural joint. That was the type of loads on the components, that aircraft component. Now this is at the structural joints, and then the aircraft inertia load. Then we will see about the aircraft inertia load. So these three things we will see in this video. So let's start with the first topic, the type of a structural joint. In general, aircraft component fabrication entails joining one part of the component to the another. So now one part to the another, if we have to join, means definitely some joint will be there. How to join that one so that it will rigid, and fix, and it won't get damaged during the flight. For example, fuselage skins are connected to stringer and frames, whereas wing skins are connected to the stringer and wing ribs. Unless the stringer are machined integrally with the wings skin, as in some military aircraft with high wing loading. So wherever the high wing loading is there, that high wing loading is what, where we can put missiles and all in the wing itself, or we can put the more payload in the wings. In that what happened? So see here, skin are connected to a stringer and frames. So how skin are connected to, means how skin and stringers are connected. Wings skin are connected to and wing ribs. So now, whereas wing skin, so this is the fuselage skin, is connected to what, stringer and frame, and wing skin connected to what, wing skin is connected to what, stringer and wing rib, unless the stringer are machined integrally with the wing skin. So unless means if it is not machined integrally with the stringers, that with the skin, then we have to separately connect. Now separately we have to connect means definitely some joint will be there. That joint we have to see. With the advent of all metal aluminium alloy construction, riveted joints become the primary method of connections, with some welding, although aluminium alloy are difficult to weld, and more recently some glued joint that use epoxy resin. So means generally what we are doing, metal aluminium alloy construction is there. So for that, riveted joint is the one of the most, you can say, used method or primary method for connecting two metals or two metal alloys or aluminium, whatever two things to connect, with some welding. Although aluminium alloys are difficult to them with some welding, but it is for aluminium alloy it is difficult, but for metal that can be combined. So more recently, what, some glued joint that use epoxy resin. So now some joint can be fixed or glued by epoxy resin also, because that also provide the enough strength to sustain. In this section we will focus on most common method of connection, that is riveting. So we'll see how the riveting is there. In general, riveted joint are stressed in complex way, and accurate analysis is frequently difficult to achieve due to discontinuities in the joint region. So because here it's not like that, here that is there. So in this wing, or suppose we are connecting something like this. So here that joint will be there, here that joint will be there, here. So this is not continuous, up to this part only it is, right? Now after this, here there is no effect of that one. Then again at this point it is there. So it's not continuous, like from here to here we are riveting. So because of that only it's a difficult to find out. You can see the complex way. So to complex way, and accurate analysis is frequently difficult to achieve, and just because of that accurate analysis is very difficult, because of the discontinuity in the joint region. The assumptions about joint behavior are fairly crude, but when combined with experience, safe design are produced. So assumptions that can be made, like this and that, but when that should be in the structure, or when we are combining with the experience, then safe design must be produced. Then only that we will see in that what is safe design, safe load. That safe design must be produced. Now type of structural joint. So first one is simple lap joint. Two thick plates connected by a single line of rivet. Two thick plates. One plate, another one, another plate. Okay, by a single line of rivet. Single line. Along this only the rivet is connected. This type of joint is known as lap joint. Means what? One over the other. Lap means what? Generally we are saying we are taking baby on lap. Means on that one. So one is there, over that put another one and fix here with single rivet. Okay. Assume that the plate have age load of P per unit. Age load. So they are just experiencing if suppose P unit that is acting on that one. P load per unit. That the rivets have a diameter P. So see, P load acting on the rivet. D is the diameter of the rivet and are spaced B. Yes. Here one rivet is there, here one rivet is there, and here one rivet is there. So in between this, what is the distance is there? The gap between two rivets is what? That is denoted as simply B apart, and that the distance between the line of rivet and the edge of each plate is A. So line of rivet and this distance that from the plate is A. Rivet. So just see, remember, you have to remember this one. Based on that only later we will see use the formula and that we can use. So rivets can be grouped on each side of a joint to maximize the joint's efficiency. So repeat what happened. They are just grouped so that their efficiency can be increased. So rivets can be grouped on each side of a joint to maximize the joint's efficiency. Assume that two plates are connected with 6 rivets on each side. So two plates are there and it's connecting 6 both the side. If each rivet is assumed to be equally loaded, the single rivet on the line AA along the AA. So line AA will take 1/6 of the total load. So that 6 part is there, right? And so one will experience what? 1/6 of that one. So two rivet on the line BB share 2/6 of the line. So whatever the line is there in that, okay. So here 2 rivet only means total 6 are there. So 2/6 load will experience by this one. Third, fourth, fifth. So third will experience 3/6 of that one. So like 1/6 each will experience. The two rivets on the line BB share 2/6 of the load, while the 3 rivets on the line CC share 3/6 of the load. So whatever that, how many rivets are there, based on that. The area of plates, okay, plates cross section is reduced by 2 rivet hole on line BB and by 3 rivet hole on line CC, so that the joint is relatively as strong as these sections as it is at AA. So AA shares only 1/6 of that one, but BB shares what? 2/6. See, 3/6 of that one. So that having difference. So what about the AA that is there? That much only it should be there. As a result, the joint is more efficient than if the rivets were arranged in 2 parallel row or 3. So like that's why we are putting rivets like this. Okay, not simply like somewhere randomly. So in parallel only we are putting the rivets so that their efficiency will be increased. Now the type of structure that is. So riveted joint with eccentricity loading. Eccentricity means what? At some particular distance already, or that we will see in this one. The bracket connection carried a load P offset from the rivet group's centroid. The bracketed connections carries a load P offset from the rivet group. So whatever is there, like here, okay, rivet is here, right, and offset from this one. That offset only how much is there? That is called the only eccentricity. If suppose that we are representing by E. So this load is acting here. Okay, then what effect will be on these rivets? Following that, the rivet group is subjected to a shear load P through its centroid and a moment of torque PE. P into E. Remember, this is not P subscript E. It's a PE, where E is what? Eccentricity about its centroid. So centroid means what? Whatever the moment will be, the moment is what? Force into perpendicular distance. So from the centroid, what is the distance? E. What is force? P. So force into perpendicular distance, moment, or force into distance, torque. The shear load P is assumed to be distributed evenly among rivets. The shear load, whatever effort is there, means those evenly should be distributed in 4, resulting in a shear force in each rivet parallel to the line of action of P. So because of that, all are sharing the same amount, then the line of action will be along the what? Parallel to the rivet or parallel to the P. The moment P into E or PE is assumed to generate a shear force S in each rivet. So because of that moment, what happened? They are producing a force or shear force S in each rivet with S acting perpendicular to the line connecting a specific rivet. So now where this S will act? S will act where? Perpendicular to the line connecting the specific rivet. So line connecting the rivet 1, 2. So now this will act perpendicular to this one. Okay, rivet to the centroid of the rivet group. Okay, so wherever the centroid, suppose here is there. Okay, so that will act here vertically. That should be perpendicular to the line of action. So just here, this is perpendicular here. Okay, it's a 2D, but actually generally if like 4 rivets are here, so this will act like this. Furthermore, the value of S is assumed to be proportional to the distance between the rivet and the rivet group centroid. So distance between the rivet, okay. So suppose here one rivet, here, and these rivets having centroid here. So that S depends on what? This one, okay, this one, and this distance. Okay. Furthermore, the value of S is assumed to be proportional to the distance between the rivet. So S, you can say S is proportional to the rivet distance and rivet group centroid. And now rivet shear. So that is type of loads on a structural joint. So first is what? Rivet shear. That shear load on the rivet because of or shear load on the rivet only. Rivet may fail due to shear across their diameter at the plate interface if the maximum shear stress that the rivet can withstand is tau 1. So what is tau 1? Tau 1 is the maximum shear that can sustain. Then failure will occur when PB, okay, is tau 1 into pi d square by 4. So pi d square by 4 is what? Area. Okay, so area, force by area is what? Pressure, right? So the shear that rivet may fail due to shear across the diameter at the plate interface if the maximum shear stress that the rivet can withstand is tau 1. So how much that can sustain? That as tau 1. Then failure will occur when? So this maximum it can stand, and now if we will multiply something more than 1, right, more than 1, because pi already is 3.14 and d square is there. So based on the diameter, definitely some value. If this value is more than 1, then what happen? Then failure will occur. Okay, so from here what we will get? PB equals to pi d square tau 1 by 4. Just it's a simplified form of this one. Okay, so this is PB is pi d square tau 1 by 4. Now second one is bearing pressure. Due to bearing pressure, either the rivet or the plate may fail. If PB is the pressure, then failure will occur when PB by P into B. P into B by T into D, that is equals to PB. What is PB here? PB is this pressure because of that fails. So PB by TB equals to PB. So from here what we can say that P equals to, from this P equals to PB into TD, T into D by B. So this here PB TD by B. Okay, so that will be the pressure. If PB is the pressure, this pressure, that bearing pressure. Next is plate failure in tension. The presence of rivet holes reduces the area of plate. So once we make the hole, what happened? Right, that area of the plate got reduced. Means what? Just here. Once we make the hole, now this part got removed. right? Once it get removed means now the total surface area got reduced. Okay, as a result, if the plate's ultimate tensile stress is UILT, failure will occur when? So now lesser area will be there, and what is that? Ultimate tensile stress, that depends on stress means depends on the area. Now area will be lesser and this have more, so before that it will get fracture or it will fail. So how that will fail? So PV by T into B minus D, that is only the sigma ultimate. Okay, sorry, actually this is sigma ULT. Okay, this is sigma ULT, that's sigma ultimate, or you can say the ultimate stress. So from here what we can say, again we can find this P. So just take this one. So P will be cross multiply. P will be equal to sigma ultimate into T into B minus D. That is PB. Right. So P will be equals to sigma ultimate into T into B minus D by B. So this will be the value of P in case of plate failure because of tension. Now, shear failure in plates. Shearing of the plates on the plane CC may occur, causing the rivets to be dragged out of the plate. So, dragged out of the plate, that because of that shearing will be there. If the maximum shear stress at the failure of the plate's material is 2, if suppose just that material is 2, then this type of failure will occur when? So, just here, this is not the maximum shear stress at the failure is 2. So, that is the PB value. Okay, then PV equals to 280 into, sorry, maximum shear stress is here, this is tau 2. Okay, so this is tau 2. Then this type of failure will occur when PV equals to 280 into this maximum shear stress tau 2. Okay, so from here what we will get? That again same, which gives P equals to 280 tau 2 by B. Okay, so this is not 2, this is tau 2. Now the joint efficiency. The efficiency of a joint or connection is determined by comparing the actual failure load to the load that would apply. So let's see, actual failure load means the load at which actually it will fail, and the load that would apply if the plate had no rivet holes. Means now first rivet hole and without rivet hole, the ratio of that is called as the efficiency. Means if rivet hole is not there, then what is that efficiency? And when rivet hole is there, then what is that? The joint efficiency is then given for the joint Y. So this is the joint efficiency. Okay, that is sigma alt into T into B minus D by B. So this is what? Yeah. Okay, so this is plate failure tension and divided by what? Just sigma alt into T. Right. So just here now sigma alt into T. So sigma alt cancel, T cancel. What is now? B minus D by B. So that efficiency will be B minus D. So just here, this smaller one is there. So as much as this D will be more, okay, this value will be less, and that much efficiency will be lesser. So what was D? Just see once again. D is what? Diameter. Okay, so diameter, if diameter will be big, okay, then what happen? Efficiency will be less. As much as the bigger diameter will be there, that much lesser efficiency will be there. That's why you can see the rivets are all of a small size, not a very big. Instead of putting bigger rivet size, okay, they are putting just a small size, that many numbers. So the same for covering same area, just put a small size. So the efficiency will be more compared to this bigger one. How to calculate that? B minus D by B. B between two rivet distance, D, and divided by that B. Okay. Now the inertia load on aircraft. Maximum load on aircraft's structural component generally occurs when the aircraft is undergoing some form of acceleration or deceleration. So simple word you can say that during takeoff and landing. Okay, such as acceleration or deceleration such as landing, takeoff and maneuver within the flight and gets enveloped. Okay, that time they will experience the maximum load. As a result, the inertia load associated with these acceleration and deceleration must be calculated before designing a structural component. So before designing a component, how much strain should be there, how much inertia load will act, okay, and because of how much acceleration and deceleration we can do in that one. Okay, that first we have to calculate. For this purpose, we will assume that an aircraft is a rigid body with a rigid mass m. So for that mass only, need to find. At this point, we will also consider motion in the plane of mass. Motion in the plane of mass. So now here mass also we are moving. That mass is moving in that plane, which corresponds to pitching of the aircraft without roll or yaw. So now once mass will move, means definitely it will pitch instead of rolling or yawing. We will also assume that the mass center of gravity has coordinates xy. So that's a CZ. Okay, CZ is assumed as what? X comma y, referring to x and y axis with an arbitrary origin O. So from origin O, that coordinate of that CZ is x comma y. The mass is rotating with a constant angular velocity about an axis through O perpendicular to the xy plane. So now that will move along the O in the perpendicular to the xy plane. So the acceleration of any point R from O is 2r. The acceleration of any point from R is 2r and is directed towards. So as a result, the inertia force acting on the element, okay, that is in the opposite direction of acceleration. The component of the inertia force, that is just here, delta m, is what? Omega square r into delta m. The component of the inertia force, that delta m, that mass because of that, and y-axis r and omega square r delta m into cos theta respectively. X-axis is omega that dm, and for that cos theta respectively, or in terms of omega square delta m sin theta, right? Omega square r delta m sin theta, either in terms of sin theta and cos theta. The resulting inertia force Fx and Fy are then given by x and y. So in the direction of x and the direction of y. So that x and y will be what? Omega square x del m and omega square y del m. So for finding what? Just integrate. We'll get that one. So Fx will be equals to, along the x-axis, omega is integral of omega square x dm, and just which is what? Omega is constant. So take omega square out of the integration, omega square x dm. Okay. So now Fy is what? Omega square y dm. So again, after taking omega square out of the integration, omega square y dm, in which we observe that the angular velocity is constant and can thus be taken out of the integral sign. Okay. So delta, that integral x dm and integral y dm are the moments of mass. So this is what? Moment of mass, or we can say mass moment of inertia, that m, about the y and x axis. So Fx is that Fx, okay. So x dm is about x axis and this is about y in the wave expression. Show that now. So for this, what we can write? Yeah, that y dm, x dm is moment of inertia of mass. So x bar m, okay, that moment m into that distance. Similarly for m moment, m into that distance, where x bar, y bar is what? That cz, that coordinates. Okay, so this is for Fx equals to omega square x bar m, and Fy is omega square y bar m. Okay, so these are the forces, that inertia load acting on the aircraft. Okay, so just see quickly once again. Okay, so first one was type of structural joint. So in that different types are there. What are there? Let's see. Joining part of the, okay. So aluminium alloy riveted joint becomes the primary method of the connection. So that is the most primary, but somewhere that epoxy resin also has used as glue by some other method also, but mostly we are using as the riveted joint. Okay, then most common method of connection is riveting right? Some assumptions are there. What are the assumptions? With that safe design will be there, then fairly it should be crude. Okay, next, simple lap joint. Lap is one over the other. So in that, what assumptions was there, or what we that means assume P per unit load is acting, okay, and the rivet diameter is D, that they are spaced apart by B, okay, and that the distance between the line of rivet and edge of each plate is A. So these are just for measuring that distance, how to find that already we had seen the formula. So this is important to remember, that what is D, what is B, what is A. Okay. Okay. So now for by grouping the rivet, we can maximize the efficiency. That also we earlier I discussed how to. So this one. So after that, the riveted joined with eccentricity loading means that rivet is somewhere here and load is acting here. That is called, and this distance is here. That is called the riveted joint with eccentric loading. Not at that rivet only, that load is acting somewhere away from the this one riveted joint, and that is called the eccentric loading. Then now rivet, so here will be what, PV equals to tau 1 into pi d square by 4. What is the diameter of the rivet? So depending upon, so that's why if this d will be more, in this case what happened, that PV will be more, but for the efficiency the d should be less, and that's why, so what we can do, instead of keeping 1, so bigger diameter, just keep more. So this total pi d square by 4 will be more, and hence this will be more. So after solving this, what we got, the simply simplified way is PV equals to pi d square tau 1 by 4. Now next is bearing pressure, that is P into B divided by TD, which gives PB. Okay, so this PB, where is that one? Yeah. Okay, so from here now we can find this P. So P will be equals to what? PB into T into D by B. Next is what? Plate failure in tension. So because of the plate failure, what will be the ultimate tensile stress? That sigma ult will be what? PB by T into B minus D, which will be equals to the sigma ultimate. From here what we can say, again we can find P. So P will be equals to what? Sigma ultimate into T into B minus D, and this V will get divided here, right? So this is here. So finally P will be equals to sigma ult into T, that sigma ultimate into T into B minus D by B. Okay. Next is shear failure in plane. So you see a shearing of the plate on the plane CC, that along that one, may occur, causing the rivet to be dragged out of the plate. So dragged out rivet, just then what happened? Okay, that shear will act that way. So how? So what happened? This is tau 2. Okay, so sigma, the maximum shear stress at the failure of the plate material is tau 2, just we are experiencing. Then what happened? That PB equals to 2AT into tau 2. So what will be the P? 2AT tau 2 by B. So P will be equals to 2AT into tau 2 by B. Next is joint efficiency. So joint efficiency will be equals to what? Sigma ultimate into B, that here, right? This divided by sigma ultimate into T. So after cancelling, what we will get? Joint efficiency will be this get cancelled, B minus D by B. So just see here, if D will be more, then efficiency, this value will be less, and hence efficiency will be less. So that's why instead of keeping the bigger size diameter, a small size, and but what we are required to require more number of areas also, that in starting already we had seen this here, this one, right? So that's why we can keep number of rivets instead of one bigger rivet, so that the efficiency becomes the maximum. Okay, now next is inertia load. So maximum loads on an aircraft structure component generally occur when they are in the acceleration or deceleration. So means at the time of landing or takeoff or maneuvering, during that time when that speed is increasing, or this one. So because of that, whatever the load they are experiencing, that is called as inertia load. So in that, what we assume, that center of gravity has coordinate xy, and xy along the xy axis along arbitrary O, in where So that is the perpendicular to the xy plane. So hence the acceleration of that will be what? 0 into 2r. For A, the component of this inertia force, that delta m, is omega square r delta m, and y-axis are omega square r delta m cos theta respectively, or in terms of, instead of cos theta, in terms of sin theta, omega square r delta m into sin theta. The resulting inertia force, that Fx and Fy along the x-axis, F along the y-axis, are then given by x and y, that is omega square x into del m and omega square y into del m. Now to find the total one, what is that? Just integrate it. So Fx is equals to integral of omega square x dm. Omega is constant, so take out of the integration, that is here. So omega square into x dm. Similarly for Fy, integral omega square y dm. So take y square out, omega square out, so omega square y dm. Now integral of x dm and y dm is what? That is the moment of mass. So for that we can write what? Integral of y dm as x bar m. So this becomes omega square x bar m here, and this becomes omega square y bar m. So this will be the force along the x-axis and force along the y-axis. That is the inertial load along the x-axis and inertial load along the y-axis because of acceleration, deceleration, okay, maneuvering and all. When that changes will be there, that time this much force will be there. Okay, so again you can refer this book, THG Mention, Aircraft Structure, Butterworth, and this is the publication, 5th edition. It's not necessary that you just go with the 5th edition, 4th edition, whatever, almost just they changes, they added some more numericals. So whatever the Mexican book you are getting, you can just use that one. Theoretically it's a same. Only the thing is, in newer book or in the old book, difference is some number of problems is there. Okay, so whatever book you are getting, you can just refer it. Okay, but that is from the THG Mexican. So if you have any doubt, you can just comment on the video or you can contact me so that I can clarify your doubts. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.